Hello, everyone. In this lesson, we will share a case study on sponge city construction, the application of lead technology in a residential community in Chongqing. Traditional urban construction models feature hardened surfaces and roofs everywhere every time it rains heavily. Drainage mainly relies on urban pipe networks and pump stations. This often results in flooding during rains and sudden transitions between drought and flood. The concept of building sponge cities that naturally store, infiltrate, and purify water using the low impact development LID concept, which is abbreviated as LID. This changes the traditional approach to urban rainwater management by harnessing natural forces for drainage and enabling a city to function like a sponge, absorbing water during heavy rains and slowly releasing it afterward, achieving natural rainwater migration. This project is based on the Chongqing Sponge City Planning and Design Guidelines and the Low-Impact Development Rainwater System Design Standards. It involves the design and construction of lead technology for a new residential community in Yubei District, Chongqing, providing a reference for sponge city construction in residential projects. First, let's take a look at the project overview. This project is a newly built residential community located in Yubei District, Chongqing. The site covers an area of approximately 29,000 square meters, with a total construction area of about 68,000 square meters. The green space area is around 13,000 square meters. This project focuses on controlling stormwater runoff from hardened pavements and roofs. The lead facilities used in the Sponge City project mainly include container-based green roofs, permeable pavements, and rain gardens. Next, let's analyze the original site's vertical layout. The original terrain of this site consists of shallow hills and slopes. In its current condition, most of the site has been backfilled and leveled. The overall terrain is higher in the north and lower in the south. Most of the site area is covered by quaternary artificial fill. The surface slope angles generally range from 5 to 30 degrees. In some areas, steep banks have formed. The lowest elevation on the site is about 394.3 meters, while the highest elevation is 414.7 meters, resulting in a relative elevation difference of 20.4 meters. According to on-site investigations, there are no signs of deformation within the site or on the surrounding slopes. The area is stable. Let's first look at the construction technology for the rain garden. A rain garden is a naturally formed or artificially excavated shallow depression in green space that is commonly used to collect and absorb rainwater from rooftops or ground surfaces. It filters, purifies, and infiltrates water through its structural layers to achieve rainwater management functions. The main structure of the rain garden in this project, from top to bottom, includes a storage layer, a cover layer, a planting soil layer for vegetation, and a gravel infiltration layer. Regarding the storage layer, it is located at the top of the rain garden structure, and its main purpose is to store rainwater, allowing sediment in the rainwater to settle effectively, and removing some organic matter and metal ions. The height of the storage layer should avoid affecting plant growth, and be calculated based on the actual control volume. In this project, the depth of the storage layer in the rain garden is 10 to 30 centimeters. The cover layer consists of 3 to 5 centimeters of bark. To maintain soil moisture, reduce rainwater's erosive effect on the soil, and provide a suitable environment for microbial growth, which helps in the degradation of organic matter. The vegetation and planting soil layer consists of sandy soil with a high permeability coefficient. The depth of the planting soil depends on the type of plants used. Typically, herbaceous plants require a depth of 25 centimeters, while shrubs require 50 to 80 centimeters. In this project, the planting soil layer has a thickness of 50 centimeters. Not all trees have been planted. As for the gravel layer, the gravel size does not exceed 50 millimeters, and the gravel layer thickness is 20 to 30 cm. A DN 150 mm perforated pipe is embedded within the gravel layer. The infiltrated rainwater is collected by the perforated infiltration line pipe and directed into the site's rainwater drainage network. In this project, rainwater is collected and flows into the rain garden via the surface channels. The catchment surface has a slope of 5%. Pebbles are used for energy dissipation at the rain garden entrance. The overflow inlet and drainage blind pipe are wrapped with permeable geotextile. The rain garden, located near the building, has a fully enclosed impermeable membrane at its base. Anti-slip measures are applied to the pavement surrounding the rain garden, and safety railings and warning signs are installed. Next, let's look at the construction technology for permeable pavements in this project. Permeable pavements utilize a permeable substrate to enhance rainwater infiltration, conserving water resources, while mitigating the urban heat island effect. In this project, the permeable pavements include pedestrian permeable pavements and vehicular permeable pavements. Rainwater quickly infiltrates through the permeable pavements and is filtered through the soil to the infiltration layer, from where it is discharged into the site's rainwater drainage network via infiltration blind pipes. This effectively reduces rainwater runoff and the concentration of rainwater pollutants. Let's first look at the pedestrian permeable pavements. Pedestrian permeable pavements do not have high load-bearing requirements for the surface and permeable base layers. Therefore, in this project, the main structure of pedestrian permeable pavements is relatively simple. From top to bottom, it includes a permeable surface layer, a leveling adhesive layer, a permeable cushion layer, and an impermeable membrane. The permeable surface layer is made of 60 mm thick silica sand permeable bricks. The leveling adhesive layer consists of 30 mm thick dry, stiff cement mortar. The permeable base layer is 150 mm thick C20 no fines porous permeable concrete. The permeable cushion layer consists of 150 mm thick graded gravel with embedded permeable blind pipes. Next, let's look at the vehicular permeable pavements. According to the building structural load curve requirements, vehicular permeable pavement should support a load of 15 tons for fire trucks. In this project, the surface and base layers of vehicular permeable pavements were designed to meet load-bearing requirements. The main structure, from top to bottom, includes a permeable surface layer, a permeable base layer, a permeable cushion layer, and an impermeable membrane. The permeable surface layer uses permeable asphalt, with a thickness of 4 cm on top and 6 cm on the bottom. The permeable base layer is made of 200 mm thick C30 no fines porous permeable concrete. The permeable cushion layer consists of 250 mm thick graded gravel with embedded permeable blind pipes. Next, let's take a look at the construction of the container-based green roof. A green roof refers to the implementation of green planting on the roof of a building. The Chongqing Public Building Energy-Saving Design Standards require that the green roof area for residential buildings should not be less than 30% of the total plantable area. In addition, the building structural load code stipulates that the load above the waterproof layer of the roof should not be less than 1 kN per square meter. In this project, all the roofs are flat roofs. The roofs are entirely covered with container-based green roofs. In roof greening, the use of planting containers is very common, with common examples being jars, boxes, and wooden crates. In this project, the structure of the container-based green roof consists of planting containers, planting soil, and seed-down. The planting soil has a thickness of 100 millimeters. The selected plant, seed-down, is drought-tolerant and easy to maintain. We have now introduced the mainly construction technologies used in this project. Next, let's look at the maintenance of the low-impact development facilities after the project is completed. Specifically, the maintenance of the low-impact development facilities. First, let's look at the rain garden. Regularly inspect the inlets and overflow outlets. If any blockages or flow issues are found, the sediment should be promptly removed. The following measures are mainly taken. The thickness of the planting soil should be checked annually. Add planting soil to the design thickness as needed. Second, when transplanting or replacing plants, quickly complete the tillage of planting soil. To minimize the exposure time of the soil, during soil exposure, cover the soil surface with a film or other protective layer. To prevent erosion by rainwater or wind, if significant erosion or loss of planting soil occurs, analyze the causes and correct them. If the rainwater drainage time exceeds 24 hours, replace the planting soil and geotex layer. Maintenance of the permeable pavement is as follows. After the permeable pavement is open to traffic, carry out comprehensive maintenance of the permeability function every 6 months. For roads with a significant decline in permeability, conduct comprehensive maintenance of the permeability function every quarter. Use a stiff broom to promptly clean moss from the surface of permeable pavements. Remove fallen leaves as soon as possible when they are dry. Remove any obstructions from the voids in the permeable pavement surface. Use a vacuum cleaner or a permeable pavement washer. Fill with high-pressure water for periodic cleaning. This should be done once a week. Focus on sweeping the edges of the pavement. Maintenance tasks for the structural performance of permeable pavements mainly include repairing cracks, potholes, settlement, spalling, and wear. The maintenance frequency should be once a month. Damaged permeable bricks should be promptly repaired or replaced with the original permeable material or a material with equivalent performance. Conduct repairs or replacements is necessary. 4. Permeable pavements with underlying drainage pipes or channels. Regularly inspect the pipes or channels for blockages, misalignment, or fractures. The inspection frequency should be once per quarter. If the pipes or channels are blocked, follow the relevant provisions in the Urban Drainage Pipeline Maintenance Safety Technical Regulations. To conduct pipeline clearing, repair, or replacement, maintenance of the container-based green roof is as follows. Regularly check the growth status of the plants. If any plants are dead, or planting containers are damaged, they should be promptly replaced. During dry seasons, water the plants appropriately. To supplement moisture, regularly spray pesticides on the plants. Set up a warning sign when spraying pesticides to prevent poisoning of humans or animals. In summary, the low-impact development facilities in this project mainly consist of container-based green roofs, permeable pavements, and rain gardens. In light rain conditions, rainwater can naturally infiltrate through the green roofs, permeable pavements, and rain gardens. During heavy rain, excess rainwater is discharged through overflow outlets to ensure safety. With the joint efforts of all parties involved in the construction, various difficulties during the construction process were overcome, and the project was successfully completed and accepted. During its usage, the relevant facilities have been well maintained, and this project continued to operate effectively. In this lesson, we use the residential community in Chongqing as an example to introduce the construction and maintenance of container-based green roofs, permeable pavements, and rain gardens as Span City low-impact development facilities. This provides a reference for Sponge City project construction. The Sponge City is a new generation urban stormwater management concept that enables the city to breathe like a sponge, reshaping the urban water cycle system. It is a vivid practice of building an ecological civilization. In China, residential areas account for 40% to 50% of urban land use, making them key to Sponge City construction. Residential communities are where we all live and reside. Therefore, let us join hands and start from our surroundings by consciously applying Sponge City concepts to build residential communities into beautiful, livable, and happy sponge communities and sponge neighborhoods. Let us work together to protect our green waters and lush mountains. That's all for this lesson. Goodbye, everyone.